All right, let's jump right in. We're going to dive into a mystery that's right at the very heart of modern physics, a debate that really makes you question what we mean by reality itself. So think about this for a second. Are parts of our most successful scientific theories just convenient fictions? I mean, it's a wild thought, right? We've got these incredible theories. They describe the universe with, just stunning accuracy. But what if some of the mathematical tools we use to build them, some of the absolute core pieces of the equations, don't actually correspond to anything real? Are they just phantoms, ghosts in the machine? Or are they fundamental parts of our world?
Okay, so to really get to the bottom of this, we got to talk about something called gauge theory. Now, the easiest way to think about it is like it's the fundamental rule book, the operating system for all the universe's forces. And inside that system, there's this one specific mathematical tool called the gauge potential. And this is what everyone's been fighting about. For over 100 years, physicists, philosophers, they've all been asking, is this thing real? Is it a profound truth about the universe or just a clever mathematical trick? Let's get into it.
All right, so this is where the great debate really kicks off.
It's this deep philosophical puzzle that's been hanging around for, well, the entire history of modern physics. See, you've got this conflict at the heart of our best theories. On one side, you could just take the math at face value. A literal reading, right? If the equations say this potential thing exists and has a value everywhere, well, then it must exist. But then you have the other side. They point out that this potential has some really weird properties that make it seem like it can't possibly be real. They argue it's just an illusion, some mathematical clutter that we should be ignoring.
So to really get why this is so controversial today, we actually have to rewind the clock.
Let's go back to the 19th century, when this potential thing first shows up and gets almost immediately thrown out. It starts off pretty innocently back in 1813, just as a convenient little math shortcut. But then, the legendary James Clerk Maxwell comes along and puts it right at the core of his groundbreaking theory of electromagnetism. He calls it a fundamental quantity. But here's the crazy part. Almost as soon as he does that, these other brilliant physicists, Oliver Heaviside and Heinrich Hertz, they figure out a way to totally reformulate Maxwell's theory without the potential. And honestly, everybody thought their version was way better. And what's just fascinating is that even Maxwell himself, the guy who put the potential on the map, he ended up getting super skeptical of his own idea. He basically said, look, if you can change the math for the potential inside a sealed box and nothing, literally nothing, physically changes for the stuff inside that box, then it can't be a real physical state. It's just numbers on a page.
And yeah, that skepticism, it pretty much became the standard view for a long time. Hertz had this great analogy. He called the potential scaffolding. It's something you use to build the house, but once the house is built, you kick the scaffolding away. You don't need it anymore. Heaviside was, well, he was even less kind. He basically called it a tool for making physics more confusing than it needed to be. For them, the mission was clear. They wanted to, and this is their word, murder the potential right out of the theory.
And honestly, you can totally see why they wanted it gone. I mean, Maxwell's original theory was an absolute beast. We're talking 20 different equations for 20 different quantities. It was kind of a mess. The version from Heaviside and Hertz, so much cleaner. It was elegant, direct, and just way more practical to actually use. By just getting rid of the potentials, they tidied the whole thing up. So for pretty much everyone at the end of the 19th century, the case was closed. The potential was just unnecessary baggage. End of story. Or so they thought.
But just when it looked like the potential was dead and buried for good, it makes maybe the most stunning comeback in the history of physics.
All thanks to a new idea called the gauge principle. I mean, talk about a plot twist. The very same thing that everyone was calling scaffolding to be kicked away suddenly becomes, in the 20th century, the most fundamental cornerstone of modern theoretical physics. So what on earth happened? How did this disposable tool become the master key to the universe?
Okay, so it all comes down to this incredible new recipe for building theories. Here's how it works. First, you start with the basic math for a particle, like an electron. Simple enough. But then, step 2, you make a really, really demanding request. You insist that the laws of physics have to work perfectly, even if you change your mathematical conventions, your starting point, at every single point in space and time all at once. This is called local symmetry, and it's a huge deal. It's like saying you could redefine sea level for every single house on the planet, and yet you should still be able to describe how water flows perfectly. It's a demand that completely breaks your original equation. It just doesn't work. But, and this is the absolute genius of it, you realize there's a fix. The only way to make it work, to rescue your equation, is to introduce a new field, a field that compensates for all those local changes. And guess what that new field you were forced to add turns out to be? It is the force field. It's electromagnetism. Suddenly, the potential isn't just a handy tool anymore. It's the essential ingredient you are forced to invent to make the universe obey this beautiful, deep symmetry. It's the glue.
So the potential is back with a vengeance, right? It's more central to physics than ever before. But this, it just makes the whole mystery even deeper, because now the debate gets completely supercharged by this absolutely mind-bending quantum experiment.
An experiment that seems to show this mathematical tool having very real physical effects. And it all boils down to this one spooky question. Can something influence a particle from a place where the particle can't feel any force at all? I mean, think about that. It sounds impossible. It seems to violate everything we think we know about cause and effect.
Okay, let's walk through the experiment because this is where it gets really wild. So you take the classic double-slit quantum experiment, and you put a shielded electromagnet right in between the two slits, so it's between the two paths the particle can take. Now, inside that shield, there's a magnetic field. But here is the crucial part. Outside the shield, where the particle is actually traveling, the magnetic field is zero. Nada. Zilch. There is no force there. And yet, the potential, the math, it leaks outside the shield. And here's the kicker, the absolutely shocking result. When they change the current inside that shielded electromagnet, the quantum interference pattern of the particles outside the shield actually shifts. Something is reaching out from a place with zero force and physically changing the outcome of the experiment. It's like a ghost in the machine.
The great Richard Feynman, he just summed this up perfectly. He said, look, this experiment forces our hand. We have two choices. Either we have to accept some kind of spooky, mysterious action at a distance, or we have to admit that the potential is real in some deep, fundamental way. It's the thing that's actually at the particle's location, carrying the information even when the force field isn't. All of a sudden, that ghost in the machine was looking very, very real.
So, where does all this leave us? Well, the Aharonov-Bohm effect just completely blew up that simple scaffolding idea. And today, the debate has pretty much settled into three main camps, each trying to make sense of reality. Okay, so first, you've got the people who say the potential is significant. For them, it's a real, physical feature of the world, just as real as an electric field. But the big problem for them is, why is it so weird? Why is it so hard to measure directly? Then you have the second camp. They see it as surplus. They'd say, okay, it's part of the theory, but it has all this extra kind of fluffy, redundant information. Their big challenge? Explaining how this half-real, half-mathematical thing can have a totally real physical effect. And finally, you still have the diehards who stick to the original scaffolding view. They insist it's not real at all. But now they have the massive headache of trying to explain the Aharonov-Bohm effect, and so far, no one's really cracked that nut.
And this is the bottom line, really. This isn't just some technical squabble for physicists in a lab. It's a debate that pushes right up against the boundary of what we even mean by physical reality. When our absolute best, most successful theories of the universe rely on these mathematical parts that we can't definitively say are real, what does that tell us? It forces us to ask that age-old question, where does the map end and the territory begin? It's a profound question, and it's why this great debate in physics is nowhere near over.